Hi, welcome to our course on Explainable AI Theory, Application, and Research. In this lecture, we will learn about SHAP. SHAP is a very commonly used method within Explainable AI for explaining the features which contributed maximum towards an ML model making a certain prediction. So we'll learn the basics about SHAP, and in the following lectures, we'll also see how to implement SHAP for various problem statements. This is the original paper which proposed SHAP method. It was published on Archive, and currently it has almost 22,000 plus citations. I highly recommend you to go through this paper titled A Unified Approach to Interpreting ML Model Predictions. I will just give you a glance of the paper in Archive. This is the paper. Just go through it once. It also outlines a few other methods and how SHAP methods differ from other methods which are popular like LIME. We have covered about LIME in other lectures, but basically there are fundamental differences between the way LIME is implemented and SHAP is implemented. So just go through the paper, even if some portions of the paper might be mathematically heavy. It still will give you a very good perspective on from the author's side on what's the need of SHAP and how does it work. So let's have a look at SHAP from the very basics. SHAP method, also called as Shapley additive explanations, is based on the work of Lloyd Shapley. The paper which explained his method was published in 1950s, and Lloyd Shapley has also won a Nobel Prize in economics in 2012. And he was a well-recognized figure in game theory. So the Shapley method is as follows. We can try to understand the essence of this using a simple example. Imagine there is a team of 4 people called Team Robo Runners. I just put a name who competed in a robotics competition, so a physical robot making competition. And because these 4 people have 4 different skills, they made unequal contribution towards the team. But at the end of the day, they participated in the competition and they won the first prize of $10,000 in prize money. Now, if we want to distribute this prize money among these 4 people, what is the way in which we can do that? That is fair, because if one person has made significantly higher contribution, it has to also reflect in the distribution of prize money. So how can we do that? How do we establish fairness in this case? SHAP is the technique that we can use for that. But before going into that, let us look some possibilities. What all things we could potentially do for distributing the money. We could distribute the money equally. So each person gets $2,500. And is this really fair? Because this is a bit unfair towards the biggest contributor. So if one person contributed 5 times more than the lowest contributing person, then it's a bit unfair. Although they are working in a team, it is still unfair to make that kind of a split. So what is the best way in which we can recognize the individual contribution of each of these 4 people? So let's take a case where this 4th person was not part of the team. So he's a hardware expert who can assemble and build stuff, and who's a integral part of this robotics team. But let's imagine that in the absence of this person, the team of 3, which are these 3 people, could not get first place, could only get second place. And the prize money corresponding to that is $6,000. So what that means is the monetary value of this person being in the team is $4,000. So is this a good way to think about it? Does it mean that the 4th person actually deserves $4,000 and the rest of the people, maybe the rest of the people can divide the $6,000 in equal or unequal proportions? Is this correct? It is not necessarily correct or fair. And the reason for that is, so this distribution is not necessarily fair. The reason for that is if the hardware expert, who's the 4th guy, may need an algorithm expert within the team to perform really well. So the performance of hardware expert might depend on the performance of the algorithm expert. So what this shows is these individuals have some sort of interactions or some sort of relationship with each other, which actually changes, enhances, or even decreases their performance. So if we imagine the team to have these three people, first, second, and the fourth person, the contribution of this fourth person may not be that much significant because this third person is not available in the team. And what this could mean is, even though this person was in the team this time could only win third place with only $3,000 in prize money. But if you remember in the previous scenario, we were giving $4,000 of money to this fourth person, thinking that that much is the contribution of the fourth person. So this is the essence of the thought process behind how do we really recognize the individual contributions if they are working in a team. So the ideal way to do this is to consider different subsets. So first, look at the whole team. The whole team has the potential to win $10,000 in prize money. And then look at the subset, a team of these three people. Maybe that team will win $6,000 in prize money. A team of these two people. So these two people are not part of the team. Then they might be able to win $3,000 in prize money. This team might be able to win $2,000. And this team might be able to win $4,000. So there are many different subsets which we can create here. And by calculating the prize money corresponding to different subset teams, we can get an estimate of how much an individual contributes when they are part of different subsets. So we can calculate how much this fourth person contributes when this person is part of this 2-member team, or how much this fourth person contributes when they are part of a 3-member team, or as part of the entire team. So there are many such different subsets that we can imagine. So the actual contribution of this person would be a kind of a weighted average of what is their contribution as part of each of these different subsets. So we have to do that extensive calculation. And that is the essence of the SHAP method. So in summary, to calculate the individual contribution, the true individual contribution, we have to consider different subsets. In this case, we are looking at different subset of teams. And to calculate the individual's contribution in each, so first calculate the individual's contribution in each subset and then take an average of these contributions. So that will give us an estimate of the marginal contribution of each player. And this will help us distribute the money more evenly, because now there is a certain process in place. There is a certain algorithm that we are following to determine how much money each person actually deserves. And maybe the distribution of $10,000 may come to something like this. And this might be more fair than equal distribution, which does not take into account what is the contribution of each of the players, or a distribution that only takes individual contribution based on, removing just one individual and considering the rest of the team and saying that this individual had a $4,000 contribution. That is also not a good approach. So this is how SHAP works in practice. So this example of a team game did not have too much relevance to machine learning. So let's now look at the corresponding machine learning analog. So let's say we have a ML model which can predict based on a person's features whether this person is diabetic or not diabetic. The features are age, exercise duration, BMI, body mass index, whether they had diabetic parents or not, their caloric intake, which could be normalized by their body weight, etc. And let's say we have a pre-trained ML model which can actually make a prediction, and for a particular person of a few set of features. So this person may have age 65, exercise duration might be 40 minutes per week, BMI might be 23, whatever, right? So there could be some specific values for this specific patient or this person. And let's say the ML model predicts that this person is diabetic based on these values of these features. Now, how do we say which among these 5 features contributed the most towards this person being classified as diabetic? How do we say that? That is a very valuable insight, because based on that insight only we can make some recommendations. So we can say, okay, you would have been not diabetic if your BMI was 2 points below than what it is today, right? So you can make recommendations like that if you know the importance of the feature for making this person diabetic. And this insight may not apply to other people because some other person who has a BMI of BMI that is comparable to this person may be diabetic for a different reason. Maybe they are diabetic because of very, very poor exercise duration, right? So there could be different reasons why a person is primarily considered or primarily classified as diabetic. And making a global statement that, oh, age is a factor that affects somebody's proclivity or inclination towards diabetes or not, that does not help in specific cases. It's like saying if you are living in a certain country with, let's say, 75 as the average age of expectancy, and there is another person from another country whose whose country's life expectancy is 85, it still does not help us to make an accurate prediction when you look at one individual from each countries to say how long or how short they are going to live. It's very difficult. So the statistical correlation of the data corresponding to the country does not apply in the specific case, and it's not valuable. What is really valuable is to know what that person specifically is doing. So similarly here, what is really valuable is to know what features of this person is causing the prediction to be in a certain way. So the intuition behind SHAP is that when we look at the features, so in this case we have 5 features, we can define something called as feature subsets. So a feature subset example here is looking at only age, BMI, and caloric intake at one time. We won't be considering exercise duration and diabetic parents. So if you imagine the game example before, there we were not considering 1 or 2 people to be in the team at some point. We were creating sub teams by taking only a subset of individuals from the 4 people. Similarly, here we are creating a subset based on features by just not considering a couple of features. But this also has a problem. The problem is that the input dimension or the number of features will define the input dimension. And we cannot change the input dimension, right? Because that will cause downstream issues in the ML model. So we have to keep the dimension or the number of features the same. So how do we do that? We convert. So if exercise duration and diabetic parents, these are the parameters which we don't want to consider, we'll assign random values. And if this process is iterated a large number of times, basically these random values will not contribute in any way towards the model. So the only 3 parameters which will contribute towards the model will be age, BMI, and caloric intake. The effect of the random number or effect of exercise duration and diabetic parents will not be there because the values are assigned randomly. So this is how we create a subset where only 3 features are relevant: age, BMI, and caloric intake are relevant. The other 2, exercise duration, diabetic parents, those 2 are not relevant. And now let's get into the math part of the line. Here is a complex equation which might make you feel uncomfortable, but don't worry about that. I will walk us through this equation really slowly. And this equation is really just as simply, it's just a mathematical representation of what we just discussed in the previous slide. So please don't worry by looking at these symbols or looking at the summation. It's all something that you already know based on what I mentioned in the previous slide. But I'll just walk you through the basics of what this equation is trying to say. So firstly, phi I of f comma x, that is what we are calculating. Phi is the Shapley value for feature I. So in this example, let's say age is the feature. If age is the ith feature, we are looking for Shapley value corresponding to age. And this is for one particular person. So if an old person whose data is available, if their age, BMI, whether they have diabetic parents, those 5 feature values are available, we are trying to see for this person, the ith feature, let's say age, how much does that contribute towards making the prediction diabetic. So we are calculating that contribution in the form of Shapley value. So the higher the Shapley value, higher and positive the Shapley value, the higher is the positive correlation between the feature I and diabetes for that particular patient or that particular person. So phi is the Shapley value for feature I. F is the ML model. It's a black box model, right? We don't know what the ML model, we don't know how to interpret the ML model. That's what we are trying to do through this Shapley method. So F is the ML model and X is the input data point. So in this case, what is the input data point? Input data point is the value of these 5 features: age, exercise duration, BMI, diabetic parents, and caloric intake for one particular patient. Those are the input values. So the Shapley value is a function of the ML model and the particular input value. And in this case, the ML model is a trained ML model because it's making a prediction, right? We are inferencing something from it. Now, if you remember previously from the example of the robotic team, we were saying that the contribution of some person is kind of like an average contribution or some kind of a weighted sum of that person's contribution by that person being in different subset of teams, right? Similarly, that is the reason why here we have this sigma summation symbol, because we have to do summation of the contribution of feature called age when that feature is belonging to different subset features like this. So we can create different subset features in which age is part of. So you can have just age and exercise duration as 2 features, and remaining 3 features can be random values. You can have age, BMI, and diabetic parents as the 3 features, and the remaining 2 features could be random values. So there are many different subset of feature subsets that we can create in which age is a part, because age is the feature that we are currently looking at. Now, X prime, so the data point is basically that set of values of features for one particular data point. X prime is the input data point X converted into another. It is like a transformation of X. You transform it into another space so that you can manipulate or work on it. And Z prime is the subset of data points where age feature is present. So they form all the different, so in the team example, all the different combinations of the sub teams that are possible in which team the member 4 is present. So it could be member 1, member 2, and member 4. It could be just 3 and 4. It could be 2 and 4. So there are different combinations possible. So here in the subsets, since the feature I of interest is age, in all the subsets, age will be a part. Let us ignore this term for 1 second. We will just look at this term first. So as I just want to show how the subset looks like first. So subset looks like age is a feature. This is an example subset. So among these subset, this is one example where age is part of. BMI is there in the subset. Caloric intake is there in the subset. Exercise duration and diabetic parents are not there. They will be assigned random values. And first, here we are calculating the value produced by the ML model by considering subset with the feature of interest. So subset with age, which is the feature of interest. So we'll calculate the value of f of z prime, and then we will calculate the value of f of z prime without taking the feature of age. So I'll just repeat. So here we are considering a subset where age is a feature. And first we will calculate what the ML model produces as the output by considering age, BMI, and caloric intake, because this is the subset that we are looking at. Now, we will not consider age for making this calculation. So we'll assign again a random value for age. So the only features of relevance are diabetic parents and caloric intake. So this is basically essentially a subset without the feature I. So the difference between this and let's say the value of this is 60%. So the ML model says if we are looking at these 3 features, there is a 60% chance that the person has diabetes. But and then in this case, the ML model says if we are but only looking at these 2 features, the person has 15% of having diabetes. So what does this say? This essentially says that age has maybe, not exactly, age makes such a difference. So if age is considered as the feature, then the probability of the person having diabetes increases from 15% to 60%. So that much, the difference between that, these two numbers, 60% and 15%, that much is the influence that the feature of age is having in this particular subset. I hope that is clear to you. And this term is a weightage term where M is the number of features within the subset. So here there are 3 features in this subset, and Z prime is the number of subsets in which feature I is present. So the weighting parameter is defined in such a way that if there are 10 features in a subset, and within that subset, the feature of age is having a huge influence. Let's say the feature of age is having 90% influence. So the difference between this and this is very big, let's say. In that case, this number should be high, because that means although the other features were present, age had very, very high influence. So this weightage term can capture that, basically. So this is the basic mathematics behind SHAP, but this is just a representation of the idea that we already discussed in simple qualitative terms in the previous slides. So don't worry if some parts of this mathematical representation either intimidates you or you can't wrap your mind around. It's okay, because this is not going to affect your ability to implement SHAP in real world problems. But it's still good to know the math behind SHAP, because it will help you appreciate the way the method came into being, and it will also probably help you figure out if some issues is happening. So just try to observe this, try to understand this, but don't break your head if you're not able to fully wrap your mind around this. That's totally fine. So the technique of SHAP can be applied on different types of data. So in this example, we have a data set that is classifying a text into a positive movie review or negative movie review. So this is an example of text-based SHAP visualization. You can see that a given small review paragraph is divided into blue colored sentences and red colored sentences. Blue colored sentences negatively contributes to the review. So if the movie review has a negativity associated with it, it is mostly due to this sentence. That's what the blue color represents. And these numbers also shows the extent of negativity of this sentence. And the red color shows positive parts of the movie review. So you can also read and see that I went and saw this movie last night after being coaxed to by a few friends of mine. So it shows reluctance, kind of negative, right? I'll admit that I was reluctant to see, because from what I knew of Ashton Kutcher, he was only able to do comedy. So it says some negative emotions that this person had about watching this movie, but the rest of the things are positive. So this is how SHAP can show for a particular data point. In this case, the particular data point is the movie review itself, why that particular movie review was classified overall as positive. And here SHAP is showing you this is exactly why, because these sentences had positive feeling associated with it, and it had this much weightage, and this sentence had a negative feeling associated with this much weightage, but overall it's positive. This is an example of SHAP being implemented for image-based data. So in this case, this image is classified as American egret, or a speedboat, or a puck. Puck is the hockey puck, ice hockey puck. And what you see here is a different type of representation of this image, in which the red color pixels represent those pixels that positively contribute to this image being classified as American egret. So obviously the background of this image does not contribute to this being bird or any kind of animal. So those pixels have no significance, the SHAP value corresponding to all of those. So those pixels neither positively nor negatively contribute, right? So that's why they are in gray/white color. And similarly, in this example, the pixels that contribute to this being a speedboat are these pixels, and exactly those are the pixels where you will see the red positive high values of SHAP. The remaining pixels around here are not contributing positively towards this being classified as a speedboat. it neither contributes negatively, so that's why it's in gray/white color. And here you can see the hockey players and the region where puck is expected to be, I guess, kind of annotated in red. But I personally don't see the puck here. It's just hockey. The puck is probably somewhere else. Puck is that, I guess, the thing which they hit. But you can see the pixels that are contributing towards it. This background, these audience, they are not really contributing anything. So this is how SHAP can help you understand why a certain image was classified by a CNN as class A or class B. Sometimes the CNN might make classification correctly. CNN might convolutional neural network might make the same prediction as that of the label of the data, but it may be due to the wrong reasons. You must have heard of the famous husky versus wolf problem. So in husky versus wolf, a husky which was present in a snow background was getting classified as a wolf, because in the training data, most of the images corresponding to wolf had snow in it, and somehow this instead of the CNN recognizing husky versus wolf, it became a good snow recognizing algorithm. So although the accuracy was good, it was not looking at the correct thing. So similarly, you can do the same thing with SHAP. And SHAP can also be applied for tabular data. In this case, we are predicting the probability for an individual making over $50,000 a year based on a few different parameters. And what this bar plot shows is for a certain individual, how much, or rather, this is for a global set of data points, how much each of the parameters influenced in making a prediction positively towards, yes, this person makes greater than $50K. So let's look at each of this. So relationship status, I guess, a relationship status, having I guess positive value of relationship means having a relationship. So having relationship positively correlates, it has a positive value. So red, high. So this has SHAP value going up to maybe 2. And it's positively correlated with the tendency for earning more. Age is again positively correlated because all the red values are on the right side of this line. So the older you are, chances are higher you might be earning. Then let's say hours per week. So the harder you work, the potentially higher you are earning. And let's just look another one. So here you see the flipped one, or rather there was another one where blue. So SHAP value for certain, I guess what this means is for certain races, SHAP value feature. Yeah, I'm not sure what this means. I guess this means SHAP, there is not much dependence on the race, I guess. And here if you are a working class, then you have a high negative correlation. So in working class, if you are a working class, maybe you may not be earning greater than $50K a year in annual income. So there are positively correlated SHAP values and negatively correlated SHAP values. So this is another way in which we can extract information out of the final SHAP output. Now let's go into some details which will help us further understand how to interpret what the SHAP algorithm gives us. So we'll not go into the algorithm yet. We will do that later. But in this lecture, we just want to understand qualitatively what SHAP is trying to do. So there are various different types of plots which will be formed as a result of the SHAP process. So there are 10 different types of plots. Of course, there are more number of plots and more nuances, but roughly we can identify 10 types of plots: bee swarm summary plot, dependence plot, force plot, waterfall plot. Then we have bar plot, heat map, decision plot, scatter plot, image, and text plot. So in this one slide, I know that this is a crowded slide, but I just wanted to show you a bird's eye view of what all different types of plots exist in SHAP. Next, I will walk us through each of these plots one by one, so that it will also help you when we are working on SHAP and when we are producing output, so that you can also know how to read these plots. So let's go through these plots one by one. Now let us look at these plots individually. So first is the bee swarm plot summary, which we already saw. And here we can see that the different factors, age, relationship, capital gain, etc., how they correlate with the fact that whether the person has greater than $50K in income or not. So age is positively correlated. All the positive high SHAP values are to the right side, all the red positive high value. So when the feature value is high, meaning when the age is high, it has a positive correlation. And you can read it similarly for the different parameters. When you have more capital gain, I don't think it has so much influence. The relationship, it has an influence because most of the red values are on the positive SHAP side. This is another type of plot called dependence plot. The only reason why I'm showing you these kinds of plot is sometimes when you see SHAP being represented using these different types of plots, you might think, oh, are there many different type of SHAP methods? Not necessarily. These are just different types of visualizations of what we find from SHAP. Some of them might be global, like some of these plots might be describing what the ML model is globally seeing, like how globally the effect of a certain feature is. But some of these SHAP plots might be looking at the individual's instances feature relevance. So in this case, we are looking at how SHAP value of age changes with the value of age itself. So you can see that it peaks at somewhere around age 50, 55, and then it decreases. So what this shows is the individual's income tend to be low when the age is low. It can be maximum when somebody reaches some middle age, but as you get older, again, the income reduces. So that is the SHAP value, what it is showing. This is called force plot. In force plot, here you can look at the individual features and the corresponding value for one instance. One instance meaning for one person, how does that person's income, age, education, relationship, capital gain, occupation, etc., contributed to the ML model predicting whether this person has below 50K or above 50K income. And so this is meant for an individual instance, not for the whole global model. In waterfall plot, you can see the same thing. For an instance, you can see the influence of capital gain. So here, capital gain has a big negative influence. For this particular person, age has a big positive influence, probably because this person is closer to middle age. Relationship is 0. So maybe it probably means, I don't know what the value 0 means. I guess it means the relationship is non-existent perhaps, and it has a negative influence. So these are the values of the feature for that particular individual. So, and this is the way in which it is influencing these features are influencing the SHAP value. So for this particular individual, capital gain is the feature of most relevance, whereas on an average, we will see in one of the next plots that age has the highest relevance. So that's the difference between saying something globally versus saying something for an instance. This bar plot, on the other hand, displays average SHAP value for each feature. Okay, so I think indeed in this particular case, you can see relationship has an influence. And I have taken these plots from different sources. They are not all from the same source of data necessarily. Some of the plots which you will see later are from different sources. So I'm not sure if we are looking at the exact same data points. So maybe the relevance of relationship and age might be different in different plots. But the bottom line is that in this bar plot, what we are looking at is the average SHAP value for each feature for the entire data set. Whereas in the previous plot, we are looking at one particular instance from the data set. So that's the difference. But both of these are equally insightful, and ideally, this is more insightful for individual instance. That is what is more insightful than for the global, how the feature correlates with the final model output. This heat map is again a very, very nice representation showing for every single instance, how does the SHAP value change for every single feature. So on x-axis, you have around 1000 instances. Each instance is one person. So here you can think of there being 1000 people whose status of whether the person earns greater than 50K or less than 50K is being predicted. And what is being shown here on the y-axis are different features, which are data points corresponding to each of these individuals. And the SHAP value, the red color, shows whether the value is positive or negative. So here you can see that for all people or all data points after around 420, the relationship is having a negative value. So maybe the data is arranged in the order of relationship or something. Maybe all these people have relationship and all these people probably do not have relationship. Perhaps maybe that's why you see predominantly red here and predominantly blue here. Same thing goes for age, but in general, you won't be able to make anything about the exact value of age and how it correlates with a prediction. Here you just see for each instances what is the so you won't know the value of age for each of these instances, because then you will have to plot the age will be varying from I don't know 15 to 65 or 75, and for every single instance we cannot plot age, capital gain, hours per week, everything on a single 2D plot. But from this you can see that for let's say this one person, so this instance 600th instance, the highest positive correlated variable is age, because around here blue, it's dark blue, and this is blue, this is blue, this is blue. Sorry, highest negative correlated. I said positive. Age negatively correlates. Highest negative correlated, and red is positive. So, for this person, on the other hand, for people over here, perhaps capital gain is what was contributed most positively for people from instance 0 to maybe something like 20 or something like that. So that is heat map. This decision plot again shows the importance of some features, age, relationship, capital gain, etc. But according to this plot, you can see that there is a much more degree of extremes for SHAP values. Negative age has much higher negative SHAP value of 15 and much higher positive SHAP value of 10. So it probably shows that age can have, not on an average, but at least in the extremes, age can have significant influence in deciding whether a person's income is high or low. Whereas country and race, according to the data set that this plot has used, has very less relevance. Capital, loss, work class, all of these have lesser relevance in comparison to these top parameters in the extremes. And in the image plot, this we already saw. This is much easier to interpret. Red color pixels are the pixels contributing maximum towards this image being classified as a speedboat. And here again, red pixels are contributing maximum towards this image being classified as an American egret. Scatter plot, this same scatter plot we saw earlier. So this is correlation, SHAP correlation between age with respect to age. And here you see the smaller the age or lower the age, more negative the SHAP value. So these low age people have age acting as a negative influence, towards which model is making the prediction that most of these people may have low income. And for these people in the medium age range, maybe 40 to 60 age range, maybe the ML model is predicting that they have higher income because age is higher. Then text plot. This is another type of plot where if you are classifying movie reviews or classifying some text-based data, you can see exactly which words or which sentences contributed towards the classification, and you can see the extent of that by looking at the color or even looking at the value from this force plot. So you can plot the force plot together with the text plot. And that brings us to the end of all the different ways in which we can plot SHAP and derive some kind of inference. However, that being said, there are several limitations to the SHAP. It's not a universally applicable method. The first and foremost thing is the computational complexity. You might have already guessed this when I mentioned about the different subsets, because there are so many combinations of subsets possible. So let's say we have a data set with n number of features. Each feature can be present or absent in a subset. So two combinations are possible for each. Two values are possible for every single feature. So basically, if we have n features, there will be 2 raised to n number of possible subsets. And if you want to calculate SHAP by taking 2 raised to n subsets, the calculation can become so big, because if you have 100 features for every data point, then it's 2 raised to 100 is a very, very big number, or even 50 features, it's a very, very big number. And what happens is, in reality, to make the number of calculations less, you are not in reality calculating for 2 raised to n subsets. You are only calculating for much lesser number of subsets by using approximations like kernel SHAP and tree SHAP. But then these simplified versions can lead to inaccuracies in explanations. because it makes a lot of assumptions. That's essentially what the third point is also trying to say. The fourth point is the independence assumption. So when we are not taking certain features, we are assuming that this feature and the other feature are not related to each other, right? But in reality, in real world data, maybe there is huge interdependence between feature one and feature two. So it's not like we can switch on or switch off different features or assign random value to the off features. And maybe who knows if these set of feature values even make sense. Like let's say SHAP created a random value where a feature in which the true value of age is, let's say, 5, and the income as a feature, if it is not part of the subset, and then a random value will be assigned. And let's say the income for a 5-year-old is SHAP is assigning a value that its income is $300,000. It's very unlikely, right? It does not make sense in real life. In real life, age and income are probably very much correlated. So if you are just a newborn baby, you won't have any income. So SHAP may throw values which are not corresponding to the real world. And the aggregation of individual SHAP values to provide global insights is very, very difficult. You can get globally how features correlate with the outcome, but getting insights beyond that is very difficult to have a complete global interpretation. But despite these limitations, SHAP probably still remains as one of the most popular explainable AI techniques, and it is mainly because it can throw insights in the cases where these black box deep learning models whose accuracy is very high but interpretability is very low. In those cases, SHAP can really help us throw some light into what's happening in the model, why the model is making some predictions in a certain way. So that brings us to the end of this lecture. I'll be sharing the references, which is mainly the paper which I use for referencing about SHAP. The GitHub repository, there is a GitHub repo with huge number of stars, which is the actual SHAP repo, and also the website with a lot of these documentations and sample code, etc. present. So I will be sharing these three in the description. So thank you so much, and we'll see each other again in the next lecture.